Okay. So why do we need a numerical methods? It was thought that the problems which we can't solve analytically, and then for that we use numerical methods. Okay. But that is not always true. If you actually see most of the cases, the problem is analytically solvable, but because of the laboriousness of the problem, we approach numerical methods. That you will see towards all the course, that's often will come the case. Okay. So, and one important problem is. Okay, fine. So now coming to our numerical method, first part is the matrix solution. What is that point? Is because you will see matrices comes in our life every now and then. Okay, we are always end up in solving a matrix. You will see towards as we progress also, many places you will get in matrices. And matrix, if I ask you to solve a matrix equation, if the matrix equation is say something around 3 by 3 or 4 by 4, and the worst case if I give you 5 by 5, you can readily solve it on a pen and a paper and give me the answer. On the other hand, if I give you a matrix of order 100 by 100, then you will simply curse me and go off. Okay, so and most of the cases we are forced to solve huge large matrices with order of at least order of 20 by 20 or 50 by 50 and all. So now these matrices, solving these matrices become very laborious. So here, though the problem is analytically solvable, it's because the problem is laborious, we approach numerical methods to solve this problem. So I'm starting this course with that problem which is analytically solvable but laborious, and that's what you will going to see about the matrix. Okay, so I can just present you some small physical problem where you will end up in matrix equation. Fine. Can you hear? Can you see me see the screen now?
Yes, sir. Yes, sir.
Okay, fine. So okay, fine. This is a simple problem. Okay, where we will face a matrix equation type of solution. Okay, so and nobody is going to do this type of exercise ever, but anyway, still we will see. So I have three masses, M1, M2 and M3. Okay, and these masses are connected by the spring system as I shown in the figure. So this was connected to K1, K2 and K3. K3 is basically a single spring, is divided into 4 kind of thing. You got it? And K5. And now if I displace the spring, these masses by x1, x2, x3. Okay, so then if you try to balance the force, this is what you will get, right? For M1, the mass of the mass of the object will have a component W1 here, and the upward spring will have K1x, and these two springs combined it makes all these three combined it marks K3 into x3 minus, I guess I made a mistake. Oh no, x3 minus x1. Yeah, of course, this is x3. Okay? You know this problem, right? This is a very simple problem I am doing. Anyone have a doubt? Am I audible?
Yes, sir.
Yeah.
Yes, sir.
So you can see it clearly. Now you see why these numbers are coming up. So K1, x1 is the one which is the force which is acting on the top. The case of mass M1, and the weight will act downward. That's why weight is there. And these two springs will K3 will have an effect because K3 is connected to x3 and x1, and there are 4. So it makes it complete as 1. So K3 into x3 minus x1. That is the force by this spring K3, and K2 also have an effect. K2 is equal to x2 minus x1. Correct? So these are the force acting in the mass M1 downwards and the upwards. Similarly, you can find it for M2 and you can find it for M3 also. I am not going into this. It's very simple. Okay, you can see it later. I can send you this problem also. You can do that. Okay, so this is what. So now what happened? I can always equate under the stable condition. I can equate these forces. Am I right? So when I equate these forces, this is what the equation I will get. Okay, and I am rearranging so that I am taking W1 on one side, the weight on one side, all the other forces do the spring on the left hand side. So, and I will get this equation. Okay, and again by rearranging, this equation can be written in the form of a matrix. Clear everyone?
Yes.
So, this is a simple matrix equation. So, if I give you the spring constant and if I give you the masses, you can solve it analytically, okay, for the simple system. Suppose if I have a system with hundreds of masses and hundreds of springs connected to it, which is typically come in your condensed matter physics, am I right? Most of the things are coupled there. Okay, so in that case, when you take any solid or how they are all connected, when I start giving you with 100 springs and 100 masses, then you will go mad to solve this problem. Clear everyone?
Yes, sir.
So this is where, even though this matrix equation can be solved analytically, we look for a numerical solution because of the laboriousness in solving the matrix problem. So then in general, how can I write the matrix? Anyway, I put it on the screen there, if you see. So means the matrix equation is something of this form. What we call is what is it? A system of linear equations, right? What we have is called as it is there on the board. Okay. So if you remember what is system of linear equations, it means you have some m unknowns. What I written on the board is same thing I am writing: a00x0 plus a01x1 plus a02x2 plus go on up to a0, I guess it is I have taken is n. 0n xn will be equal to say something like your b1, and it keeps on going. Okay, and finally you get am0 x0 plus am1 x1 plus, so this will become amn xn, and that will be bm. All right. Okay. Clear everyone?
Yes, sir.
Yeah. Okay. So this is a system of linear equations, and this equation I can write it in the form of a matrix, which I already shown it in the slide if you see. Okay. So and then in the matrix form and in the vector notation, we will write it as matrix A into vector X will give you the vector B. Am I right? So this is the problem we have to solve. We have to solve for X given this matrix. Okay. And well, you can solve this problem. It will have a unique solution under the condition when m is equal to n. Am I right? When the number of unknowns are equal to the number of equations, then you can solve for a unique solution. Correct? Am I right?
Yes, sir.
Yeah. Okay. So we will have a okay. So let us take up a. Okay, fine. So let us try to solve on a pen and a paper a simple equation. Let us try to solve this equation. So I am going to have two equations: 2x minus 3y plus 6z equal to 5, x plus y minus 2z equal to minus 1, 3x minus 2y plus 4z equal to say some what I can say 4. There are three equations. Okay, we can solve them analytically. There are three equations and three unknowns. You can solve it. Okay, 1, 2, 3. You can solve for x, y and z. Am I right? Can you solve it with a pen and a paper and tell me the answer?
Yes, sir.
Are you able to solve?
Linearly independent and biaxial.
Yes. You will not be able to solve it, right? And can you anyone say why you are not able to solve it? Because the third equation is nothing but, correct? Am I right?
Yes, sir. Yes, sir.
So of course you are not able to solve it because the third equation is nothing but 1 plus 2. So, so now you see I have given the number of unknowns and number of equations are equal, but still you will not be able to solve the equation because the one equation can be expressed as a linear combination of any other equation. Okay, and similarly I can give you one more problem. So, similarly I can give you one more problem. You can try this one also. Say something like 5x minus 3y plus 2z equal to 6. 3x minus 3y plus 2z equal to 7. And say minus x minus 3y plus 2z equal to minus 1. You try to solve this problem, you will not be able to solve this also. Okay, though these equations, none of the equations are linear combinations of each other, but still you try to solve it, you are not able to solve this equation also. Can you try that? Done? Back?
The determinant is 0, right?
Of course, yeah. The singular matrix. Of course, you use your Kramer's rule, you will get it determinant 0. Of course, you can't solve it. Okay, and so you got it. So this is what. And you find out. So this any of the row. So this is what you call as a singular matrix. Okay, and this is what called as a degenerates. So when any of the equation can be written as a linear combination of any two equations, we call that as a row degeneracy. Okay, and in the here if you see, if the columns are the same linear combinations, all the equations, then you call it as a column degeneracy. Okay, and interestingly what happened, if you must have tried it, the moment when you are trying to either solve for these two equations, try to eliminate, say for example, try to eliminate x from these two equations and x from these two equations, you will end up in the same two equations, am I right? Correct? Respond?
Yeah.
Yeah, so when you try to eliminate x from these two equations and try to x from these two equations, you will end up in a same equation. So what happens? A row degeneracy has eventually created a column degeneracy. Am I right? And similarly, if you try to do it out, this eventually, if you try to solve from these two equations, you will end up with two equations which are row degenerate. You can try it on the pen and the paper. It's simple. Okay, so what happens is a row degeneracy will end up in a column degeneracy and a column degeneracy will end up in a row degeneracy. It doesn't matter. What I'm saying is if the matrix is singular or if it is degenerate, then you don't have this matrix equation will not have an unique solution. Okay, then you call this problem as a singular matrix. Okay, that means it can't have an unique solution, it can have more than one solutions. Okay, so this is what. So in solving the matrix, so we have to make sure the matrix is not singular. Okay, and okay, so then we can, from this discussion, we come to a conclusion. Okay, so if you remember the old matrix which is already presented on the screen, if you see that, so what the conclusion you can write is, there m is the number of equations, correct? So m is the number of equations, n is the unknown. Suppose if m equal to, if m is m equal to n, yeah, and if m equal to n, and if equations are not degenerate, we will have an unique solution. Okay, and now if so the point is, if m is greater than n, that means, or okay, let us take m is less than n. So m is less than n. That means the number of equations are less than the number of unknowns, or m equal to n but degenerate. In this case, you have no unique solution. Or many solution. Okay, and in this case, the matrix is called it will become a singular matrix. Am I right? So in this case, the matrix will become singular. Okay, and this problem is not very straightforward to solve the problem. Of course, we may need, even though it has a many solutions, we may need a very favorable solution. Okay, so this, most of the times you will face in this, the matrix will become singular and you will not be able to handle it. But you need some solution which is favorable to you. So you need to develop an algorithm to solve these equations also. So, and that algorithm which we call a singular value decomposition, okay, we will see about it. We will see about singular value decomposition after solving, after going to the simple problems and all. Towards it, I'll take you to singular value decomposition. So this is the way you can solve for a singular matrix, and this happens when m is less than n or m is equal to n, but they are degenerate. And come for the next condition. That is when m is larger than n. Believe me, this case happens many times in your research life. Your number of equations will become more than the number of unknowns. Okay. And so then and they are not degenerate So this is an important condition. That means you are having equations more than your variables or more than your unknowns. So then in this case you will not have a unique solution. And if those equations are not degenerate, then we will not have a solution at all. So not any, no solution. It will not have any solution because there won't be any set of any variable which is going to satisfy all the equation, because none of them are degenerate. So we will have no solution, and we will face this problem many times. Okay, in that case, how to handle it? We will not see this one, but there are a way. How do they handle it? You look for a solution which closely matches all the equation. It comes more like a statistical fitting procedure. You look for a solution which closely matches all the equations and choose that as your favorable solution. Am I making it clear?
Yes, sir.
Okay, fine. So these are the different types of matrices we will try to solve in this chapter. And okay, and if you go back to the screen and the presentation, and if you see there, I can just tell you. So if I swap a row, look at the matrix part. Look at the matrix part. If I swap the row and swap the row of B matrix, Okay, will the solution change? For instance, let us say I am going to swap the row 1 and row 2 and B1 and B0. Sorry, I have made it a 0. Row 0 and row 1 and B0 and B1. I am swapping it. Okay?
The solution would change.
Wouldn't change, correct. So solution, so any row manipulation is not going to change the solution. Or even if I replace a row with a linear combination of any other rows along with it, okay, so that also not going to change the solution. Am I right?
Okay, sir.
Correct. And similarly, if I swap a column and maintain the B as it is, equivalently I will swap the row of X. Still the solution is going to be same. Correct?
Yes, sir.
Right? I am going to swap a column and I am going to swap the row of X matrix. So these are the juggleries I can actually do in this matrix equation, and we will see how using this jugglery we can able to solve this matrix. And that method is what first method is called as the elimination method. Basically, you try to eliminate all the elements of the matrix A, make it a 0 and find a solution. That we will see that, and that's what we will see. It's a very simple methods, and we will see that. And yeah, before that, I want to tell you one thing when you are dealing with a computer. So for example, let us take that you are solving a matrix equation in a computer, which is say something around 50 by 50. And during this process of elimination, we do lot of manipulations with the matrices. Okay, we will see that. Lot of you must have read it also, Gauss-Jordan method and all. You do a lot of row, you keep subtracting and dividing the row, multiplying all the constants, all possible jugglery you do, mathematical jugglery do in the row. That means you are going to do a lot of arithmetic operations. Am I right? And suppose if a matrix is very big, 50 by 50, at some point in the operation, two equations can look very closely to each other. Okay, though it is not exactly, because the computer has added up the round of errors or within the precision level, two equations may appear very close. And suddenly the computer will, means either you will get a NaN, or if you are smart enough to find out a singular determinant, check whether at every instant the matrix is solvable, it starts shouting you encountered a singular matrix. But you know very well your problem defined is non-singular. Okay, so it has a unique solution. You gave the problem to the computer, and because of this round of errors and everything, it messed up your solution. In the half the way through, you got something called as your singular matrix. Okay, so one way to avoid this is, when this happens usually is when the matrix elements magnitudes are very large and small. Okay, so you have, suppose if a matrix, one of the elements is 10 to the power of 5 and another one is 10 to the power of -5, you are very prone to get these types of problems. So it's one of an advice when you are solving the matrix equation, you don't try to rescale your problem, you can actually reframe. Okay, when you have a large number, it's basically ill-framed problem. So if you carefully look how you can frame the problem such that the matrix elements are not very large magnitude numbers. And this is a general advice in a computation that you should never involve numbers with a large magnitude. It can fail many times. Okay, so and this is the reason that's one of the reasons you shouldn't, when you have a problem, you shouldn't jump into the computer and start writing the program. Take a pen and a paper, reduce the equation proper form, get it in the proper form which is the computer able to solve, because that's why I said this machine is stupid, don't think it is intelligent. It will mess up your problem as much as possible. So knowing its capability, try to reduce the problem to a safer state which can be given to the computer, and then you have to solve it. Okay, so this is one of the important thing we should note when you are solving the, not just the matrix, any problem in the computers.
Sir,
yeah.
would it be better if we take all the coefficients as integers, right?
Yeah, of course. See, that's why I'm saying if your problem involves only integers, use only integers. Don't go to any real number. But most of the cases it will not happen. It is very rare cases you will deal only with the integers. But yes, so
Scale all the equations.
Yeah, but when you do the operations, it can become real, na? You got it? You may start your initial thing with an integer, but when you do the operations, then you have to have an real operations.
Yes, sir.
Okay, so that was the point. Okay, so then I think shall I give a small break?
Yes, sir.
Yeah, okay, I will give a break for 10 minutes. Anyway, we already crossed quite a bit of time. So, for 10 minutes, and then we will look for some of the elimination methods to solve the matrix. Simple methods. We'll start with very simple methods.